On page 5, we're focusing on separating chemically bonded atoms or breaking bonds, and looking at the amount of energy that goes into that. So you require energy to break, so that's energy going in, and forming bonds releases energy. So we're looking at the net amount of energy. And delta H is just the difference between the two energies. So again, exothermic, you have a net gain of energy, so you have energy left over to give away. If it's endothermic, you're putting more energy in than you're getting out by the energy release from the new bonds. So if we look at something like H2O formation, we have an H to H bond, and then we have another H to H bond, and then we have a double bonded oxygen. In order to make water, we have to break those bonds. So what I'm going to do is come in and I need to break that one. So I break this H to H bond, I have to break this H to H bond, and I have to break these two double bonds here. But then what I get is an OH bond. So this is my oxygen. I have a bond to that hydrogen, and each oxygen has two of these. So this is where the 4 is coming in. There's one here and one here. And then I have the second hydrogen and oxygen set in my second water. So the amount of energy required to break these two H2OH bonds and one double bonded oxygen must be less than the energy released in the formation of my 4. And again, 1, 2, 3, 4 is where those bonds are coming from. And then all processes are endothermic in one direction and exothermic in the other. So just like we flip for electrochemistry reactions, when we change the direction, we can do this too. So if liquid to gas is positive 40.7 kilojoules per mole, then gas to liquid water has a heat of vaporization that's negative 40.7 kilojoules per mole. So our next goal is to look at determining delta H reaction from standard heats of reaction. So we have another delta H, and you'll notice this is a formation. It has a little F with the degree sign, and that is the standard enthalpy change. So again, enthalpy is heat or energy for the reaction forming 1 mole of compound in its standard state from its in their standard state. So that's a definition you definitely should know for the AP exam. So for water, from its standard state, so hydrogen is normally a gas, oxygen is normally a gas, water is normally a liquid. So that's why this is a heat of formation in standard form. There's a value associated with that. So standard states are for a gas, 1 atmosphere, for a substance in solution, 1 molar concentration, and for your pure substance, the element or compounds, that's what we're talking pure, the most stable form of the substance at 1 atm and 25 degrees Celsius. So on your periodic tables, the one on the wall or that pink one that you had last year, those phases that are highlighted would be their standard states. So that superscript that looks like a degree sign always means that things are in their standard state. And then this is another important concept for you to know, is that the standard enthalpy of formation is 0 for all elements, including diatomic elements, provided they're present at 1 atm for gaseous elements. So that's another definition they will not give you in the exam. You'll need to know that. So for any reaction, we're going to have this delta H value, or delta H reaction standard is the summation. So you'll see here this symbol for summation, if you've seen that in math, of n times the heat of formation of the products minus the sum of n times the heat of formation for the reactants. So I'll show you a sample problem with this. This information has to be given. You can't guess this. So there's an appendix in your book. So if you don't have your book out, please pause the video and get to that part of your textbook. So, sorry, you're doing products, so the 4 is from the NO2, and the 6 is coming from the H2O liquid, and for that value we need the minus 285.8 840. And these are really kilojoules per mole. So this is 6 moles. So the moles cancel. This would be 4 moles. This is kilojoules per mole. So those moles cancel. So this whole part is your products minus, and we're going to need to do the reactant part. So this time the 4 is actually from the NH3. So minus the quantity 4 moles times the negative 459. Again, this value is coming from the chart in your textbook. Excuse me, about 45.9 plus 7 times 0. Okay, and you are going to have to show that times 0. So again, oxygen's an element in its normal state, so that's why that value is 0. They will not give you that on the exam, those you'll need to know. And if we sum all of that up, we get a total of negative 1398.6 kilojoules. And again, the reason we're keeping till the 0.6 is if you go back to each of these, this has 0.2, this has 0.8, this has 0.9, or that's the one that I messed up. That's really where your decimal point is. So since all of them go to tenths and you're multiplying by whole integers, that's why you can keep till tenths in your final answer.